So welcome everyone to this week's Origins Colloquium. It's a great pleasure to welcome Yorick Vink to give the talk this week. Yorick received his PhD from Utrecht University in 2000, I think it was, and was then working on massive stars then, as we'll hear, I think, in his talk. Then he moved to Imperial College London as a postdoctoral fellow, and then on to Kiel as a RC UK fellow. After this, he became a research astronomer at Armagh Observatory, where he's also been at a stage the director of the planetarium there. I've known Yorick for many years for his work on stellar winds, and even in my thesis, we were very interested in his results on the bistability of the winds for the mass loss. And then over the years, he's been doing a variety of topics related to stellar astrophysics and young stars and massive stars. And so, yes, it's a great pleasure, Yorick, to hear about your latest work and discuss it.
Yeah, thank you, Jonathan. So this is a little bit of a mixed talk between two different topics, but I'll try to make clear why I think they are somehow still of interest to inform each other. So when I say M dot, I always have, there's two interesting aspects to M dot to me. And one is that what is accreting onto the star, and the other thing is M dot, what is leaving the star. And I try to learn about the formation and evolution of stars using M dot, basically. This is how they are connected. And basically look at two extremes of the mass function, the T-Tauri stars at a very low mass, and then the very massive stars, basically what sets the upper mass limit. You see a number of names here. In more recent years, I've done a lot of work on very massive stars. So these are colleagues of mine, former PhD students, and currently these two are postdocs on very massive stars. And then this is some work from quite a while ago. I must say there's more than 10 years ago, some of it. Some of it's very new though, on T-Tauri stars. So let me get onto it. There we go. So basically ignore the evolved part of the universe on this side of the main sequence. So here's the zero-age main sequence. So as I said, here we have the T-Tauri stars. Here we have a paradigm for how stars form via magnetospheric accretion. But when you go up the mass range, that becomes less clear. We don't really know what kind of accretion physics is setting the masses of the stars above, I would say, the Herbig A range. I think the Herbig AE range are very similar to T-Tauri stars, but then already showed the spectropolarimetry that Herbig BE stars are probably accreting in a very different way, more via disk accretion. And then above 20 solar masses, we are much more guessing because we cannot observe the stars very close to the main sequence because it's all hidden behind dust. Although there are indications for disks at earlier phases, as I'm sure you're all aware of. So quite likely disk accretion plays a role here. Now, the other interesting thing in the last decade or so are these stars that are the super O stars, so the O stars on steroids, more massive than 100 times the mass of the sun. So they appear as Wolf-Rayet stars with nitrogen and hydrogen in the spectra, but evolutionary, they're core hydrogen burning. So these are the upper mass stars, not the O stars. They're not the earliest type stars, O stars. It's really these stars. So this is basically, if you forget everything about this talk, then at least think about this plot. If we observe stars, like in R136, a young cluster at 150 solar masses or so, after maybe 1-2 million years, we may observe stars at 150 solar masses, but that doesn't mean that these stars initially were 150. We can, in fact, not really distinguish between what was initially a 200 solar mass star or even a 1,000 solar mass star. And I'll come to this. The mass loss is so strong that the most massive stars have stronger mass loss rates than the lower mass stars. This is all due to the fact that these stars have a very strong Eddington-dependent mass loss rate. I'll come to that. But it all basically converges to the 1 point here. Now, this is for evolution post zero-age main sequence. But this physics of these winds, this will not just kickstart when the star starts to burn hydrogen. This will already happen during the pre-main sequence. Now the question is, what is the balance between how much mass you're accreting and how much wind mass loss you have. And when I included in my 2018 paper here, included mass accretion rates of 10 to the minus 3 solar masses per year, which I took from the literature, and we can discuss that number. But at some point, these mass loss rates become so high that they become stronger than the mass accretion rate. So I would say that is then what would set the upper mass limit. And I would then expect, because of the metallicity dependence of these winds, I would expect the upper mass limit to shift to higher masses at lower metallicities. So lower metallicities, of course, there's a whole range of metallicities in the universe. We go from the Big Bang, where you had no metals, and then the first stars, population 3, where you only had hydrogen and helium, you had probably very little mass loss. And then we have galaxies like the Milky Way today, which have mostly solar metallicity, though in the outer regions of these spiral galaxies, you might have lower metallicity regions. And I'll come to that in a moment because I know you're interested in it. For instance, SH2-284 is low metallicity in the outer range of this galaxy. And then there are nearby dwarf galaxies like the SMC, the LMC, which also have lower metallicity. So we learn something about this by studying stars nearby. And what we really want to find out is, how did star formation go from here to here? Now, I'm sure these are topics you're very interested in. What I'd like to point out is that people often talk about that the population 3 stars were more had higher masses because of the cooling effect, so that the hydrogen H2 was the only coolant and CO wasn't available yet, and that give you higher mass stars for POP3. But as I said, if this wind physics is important, then that is not just something between POP3 and the rest, but this is something that is continuously happening when you go to earlier and earlier in the universe. So a brief outline, the role of very massive stars, very massive star formation, just a few words about that, evolution, and then in the second part, I talk about our assumptions about the mass accretion rates, and can we learn something from lower mass stars? So what is the most massive star in the universe? Often people 10, 20 years ago had stellar models only up to about 120 solar masses. But there wasn't very good fundamental reason why that was the real limit. It is something that may follow from the next part. If you assume just electron scattering, you might come to something like 120 solar masses. But we need to consider all the opacity. So when we look at the formation of a star, we look at the balance between the radiative acceleration outwards, which is given here. The flux is for L over 4 pi r squared, and you need to balance that against gravity. And then you can write down your Eddington parameter, the balance between the two, just a number of constants down here. So you have the L over M ratio times this opacity. Now this opacity looks very innocent. In the formation of the star, far out, this is usually the dust opacity. But if you get close to the star, where it's ionized, you get electron scattering opacity. But you get more than that. You get line opacity. You have an outflow where you have additional opacity due to radiation during winds. And that is what I will want to talk a bit about in a moment. Now, for the theory of star formation, 3-4 decades ago, people thought stars could only form via disks, just form from single stars up to about 10 solar masses, because the radiative acceleration of the dust opacity and gravity were balanced at about 10 solar masses. But it was in 1D now. But we knew there were 50 solar mass stars. So how do you get 50 solar mass stars? You have to merge them. Now, that is still possible, of course, but maybe that is no longer a requirement, because with multidimensional models, people have been able to accrete material over the equator and the radiation escapes over the poles. So you can basically sneak the material into the equator, and you can potentially via disks form unlimited masses. There's no really fundamental reason, I think, in this mechanism of what the upper mass limit is. You just need to start with enough material in your original cloud, and you would end up with a more massive star. So that doesn't really set the upper mass limit. Maybe the stellar winds will. Now, from observations, theoretically, you can look at what is the most massive star, but also you can, of course, look at observations. Now, if you want to find a big star, you look in a big cluster. This is the biggest cluster at 50 kiloparsec in the LMC, R136. And it was once thought to be a 3,000 solar mass star, but then when people did higher and higher spatial resolution, it broke up in A1, A2, A3, etc. Now, these stars are still very luminous, of order 10 million luminosities of the sun, and these are 200, 300 solar mass stars. And these stars are not going to resolve even in smaller stars. They might still have tiny little companions, but it's not the case that one 300 solar mass star will break up into 10, 30 solar mass stars. And we know that because we have spectra. And these stars have a very characteristic emission line spectrum that is very different from normal O stars, which are dominated by absorption lines. So we know these very massive stars really exist and that there are really hundreds of solar masses. And we want to understand what they do, and therefore we need to understand this physics of the line driving of the winds. It was developed in the 70s. And basically, the more photons you have available, the higher the L, the higher the mass loss. The lower the mass, the easier it is to escape the potential L. So M plays a role, and also the metallicity, and in particular iron lines, are critical to setting the mass loss rate. So the DMDT here is definitely metallicity dependent. The winds will depend on metallicity, but not just metallicity, also on this L and M. And actually, what is really important is the L over M, or the gamma. I'll come to that in a second. So the way I calculate these winds, and there are other ways of doing it, but I use Monte Carlo methods. And in this way, you can use your photon packets to dump momentum and energy into the wind. And via multiple scatterings, you could potentially reach wind efficiencies larger than unity. That means that the m dot v infinity can exceed the momentum per second in the radiation field, which is given by the luminosity. Yeah? And that way, we can get very high mass loss rates, much higher than for normal O stars. So what we're now including in our stellar evolution models is if we have the mass loss rates versus this L over M, this gamma, then this is the normal O star range, where the old CAK theory is still valid. But then when we cross this critical point, this transition point, where the wind efficiency crosses unity, we also cross the point where the optical depth of the wind is from less than 1 to more than 1, and the winds become optically thick. So these are the O stars, and these are these O stars on steroids, the WNH stars. And for these, we need to boost our mass loss rate significantly by a factor of a few. And it has dramatic consequences for the evolution of these stars. A low mass, 100 solar mass star still wants to go to the red. But above that, 200, 300, 400, 500, 500 solar mass stars, they evolve strongly downwards. There's a downwards vertical evolution. And we can explain with our really high mass loss rate how this evolves. And this is nice because when we look in a cluster like R1V6, and we have a bunch of stars at different masses and different luminosities, but all sitting at the same temperature, it's very hard to explain that with any other mechanism. Because if you had no mass loss or very little mass loss, these stars would inflate like crazy. And if you have very high mass loss, these stars want to turn to the blue. There's a very delicate balance between inflation wanting to become redwards and wind mass loss that want to expose the helium core. And if you can do that for one mass, to do that again for another mass, another mass, another mass, is almost impossible unless you have this vertical evolution downwards. So we think there are other reasons why this is happening than just what is coming out of the calculations. But obviously, in the end, we would want to see observations of mass loss rates of these really massive stars. But for now, we have a new framework that I think gives very nice results. It also produces a lot of nitrogen and sodium, which might be important for high redshift universe, important for sodium in globular clusters, etc. Now this means, and this was the first slide, that very massive stars will evaporate. You can start with 1,000, but you end up with almost nothing. Now that is for the galactic case, but at low metallicity, this can be very different because we have metallicity dependent winds, so the mass loss rates are lower. And that is relevant because we know there are these heavy black holes from gravitational waves, which are clearly more massive than you would have in the Milky Way. In the Milky Way, the most massive black holes found from electromagnetic radiation, Cygnus X1, are about 15 solar masses. So these ones are probably coming from a lower metallicity universe. And that can be quite easily explained by these line-driven winds. If you consider the abundance and the number of lines, it turns out that simple atoms like hydrogen and carbon don't do very much, but iron has many more lines. It has millions of lines, and therefore the opacity from iron dominates this. Even though you have 2,500 hydrogen atoms for every iron atom, it is still this process that dominates. And that means we can even explain impossible black holes like 85 solar mass black holes, which is the current record holder as far as I know. And we can write down a simple sketch for the black hole mass, the maximum versus metallicity or age of the universe, where the upper mass limit here is now doubled from the old limit, which is set by pair instability supernova. That means that above this, the star has no black hole, but is blown into pieces. Whereas at high metallicity, like our own Milky Way, you have strong mass loss, and it's not the pair instability that sets this limit, but it's stellar winds that set this limit. That is the framework that we're currently working in, and I think it will be very interesting to find out exactly where this transition will occur from where the pair instability supernova dominates to where the winds dominate. Now to come back to the second part of the talk, that is really about the accretion rates. Now, what accretion rates should we use for very massive stars, and are they metallicity dependent? I really don't know, but I'd like to first think about, do we know anything about accretion rates, even for low mass stars? Now, for T-Tauri stars, there's a paradigm. I'm sure you're all familiar with this. There is material coming from the inner disk onto the star. It's the magnetic field of the star that disrupts this disk here, and you get these accretion flows. And these accretion flows produce H-alpha emission. There's basically a shock here onto the surface, and you get UV radiation, but there's also line emission associated with it. And from this H-alpha emission, people infer mass accretion rates. And it has been suggested to use not just spectroscopy, but also photometry from H-alpha from H-alpha photometry, you can basically compare the H-alpha line compared to its R band next to its H-alpha line, and you could potentially get the mass accretion rate. And then if you do this for large samples of stars, and it's been done by the DeMarchi group with HST quite a while ago, and they have written down equations where the mass accretion rate varies with the age of the star, the mass of the star, and the metallicity of the star. And they find observationally that stars in the clouds have higher mass accretion rates than in the Milky Way. That is the current status in terms of before we started looking into this. I was a little bit concerned about measuring mass accretion rates at such large distances when this hasn't quite been tested yet locally. And therefore I started this with a PhD student, Geert Barendsen, now a long time ago already. But basically we used photometric galactic surveys like IVAS and VIVAS to see whether this H-alpha method, so where you look at to compare the photometry from H-alpha compared to the underlying R band, and compare that to what you can get from a spectrum. And you can have here a color magnitude diagram where R minus I is something like temperature, and where R minus H-alpha, the higher equivalent widths basically give you stronger mass accretion rates. And we've basically found a difference that the classical T-Tauri stars indeed have much higher equivalent widths than the weak-line T-Tauri stars. And yeah, this is basically something that we could potentially use. And we tested this against spectroscopy. I forgot the name of the region, but I can find it for you. But basically, when we compared our IVAS equivalent width versus the spectroscopic width, we found a decent relationship, a very good relationship, actually. So potentially, this method can be used. But it's only been tested like this at small distances. So I'm not entirely sure if it works at high distances. But basically, we continued this work with Venu, and he showed also IFAS mass accretion rates compared to spectroscopic results from the Hartmann review, and basically they fall right on it. So the mass accretion rate versus mass relation, and also the mass accretion rate versus age relation from viscous disk evolution, they're basically reproduced. So
I mean,
that is,
can I ask though?
yeah,
There is quite a large scatter there. Is that
yes.
scatter understood?
I think it's not well understood. Every time I see plots like this, there is still a huge scatter of an order of magnitude or 2 orders of magnitude quite easily. One possibility is that, of course, these columns, they're not static. They come in and out of the line of sight. So there's rotational modulation. And there will be some scatter associated with that. So that might not be a real variation in the mass accretion rate, but it might just be that the orientation
Well,
changes.
then you'd see it in temporal variability. The
Yes,
same object.
and we do see temporal variability, but I don't think that the entire scatter can be explained this way.
Anyway, we keep in mind for the discussion. Yeah, great.
Yeah. And then this is basically, I noticed that you had an interest in this region, SH284. This was now a salt spectroscopy survey a number of years ago. And if you plot the galactic, the normal solar metallicity, Orion type data, versus our blue dots here, which are the data from this region, there isn't a strong difference as far as we can tell. And therefore, we have some doubts that there is a metallicity dependence on the mass accretion rate. Now, I think this is just one study, one finding, and I think I'm not saying that the Marquis et al. Group are incorrect. I'm just saying we shouldn't jump to conclusions yet. That's all I'm saying. And I think there are interesting things we can do into the future with James Webb. We've recently, Venu has basically identified 12 pre-main sequence stars in this low metallicity galaxy WLM. It's a megaparsec away. It's far away, but potentially these red dots here, they are pre-main sequence stars where you could potentially measure mass accretion rates and test when you go to a really big drop in metallicity from solar to this region would be really a factor 10 in metallicity. That is basically what I wanted to say. So just to summarize what I've said, massive stars in low metallicity are different. That's why we are doing a big survey with VLT, the X-shooting Ulysses survey, to understand these differences in terms of the evolutionary and wind properties of these stars. From theory, I think that the upper mass limit may be metallicity dependent, and not because of the cooling effect, but because of the feedback effect from the stellar winds directly at the upper IMF. Of course, this is crucial for things like parent stability supernova, gravitational wave events, and it can be small changes in the mass loss rate that can have big differences in whether you get a horizontal evolution or a vertical evolution. And then this other interest of mine on the pre-main sequence stars, mass accretion rates might be set dependent. There are studies that show this, but there are other studies that don't. So I think this is to be investigated. And of course, can we learn about how the physics changes over the mass range from Titori to Herbig to the massive stars? So these are open-ended questions as far as I'm concerned. And yeah, we could just have a discussion if you want.
That's great. Thank you very much, Jörg. So yes, let's transition to a discussion. We have about 30 minutes for that. And perhaps, I mean, you can still show slides, Jörg, during the discussion. I'm sure we'll need to. There's obviously two main topics here. Perhaps we can try and do the accretion rates for the thing we were talking about for most recently first, and then we'll come to the very massive stars after that. But anyway, in this, see, Devesh has his hand, but that's probably on the very massive stars. That is my guess. So perhaps we can just hold that for a second. Um, I mean, in terms of the accretion rates, I mean, as stars age, of course, the accretion rate eventually goes to zero. So, in any given star, it's going to be there's going to be the secular evolution, and in a given region, so it'll be age dependent and so on. So, comparing accretion rates as a function of metallicity, one always has to build in this time aspect as well, the age of the region, and measuring ages is tricky. So I don't know if you have a comment on that. I mean, this reminds me of DeMarchi's claim that there was H alpha from 20 million year old stars on the, you think they'd be on the main sequence by then. Do you have any comments on that, Yorick? Those aspects?
Not directly. I've heard about that. It sounds a bit, yeah, old for having such strong disks and mass accretion going on at 20 million years, but I don't have any argument against it. So,
Right. Well, that was one of DeMarchi's claims from the LMC SMC. I'm trying to remember if that has been resolved yet, but I suppose at some point there's potential for other forms of H alpha from coronal activity and so on, but
I think that would generally be narrow. Yeah, okay, but in H alpha photometry, you wouldn't say that. So I think the photometric method is a good one, but I think it needs to be carefully calibrated.
But so in your IFAS survey, have you? I don't know how many stars you have in your survey, but do they extend to ages that are, do you have stars that are approaching 10, 20 million years old in certain parts of the sample, or do you have a baseline of stars that have stopped accreting?
We haven't specifically looked at an age dependence or something like that. I do want to point out there was a very recent, last week paper, I think, with the Gaia huge sample, I think 1 million stars.
Yes.
Many different star forming regions. But I haven't read the paper yet. But basically, yes, in terms of figuring these things out, having such a much larger data set will help, undoubtedly. The question still I have often on my mind is, are we really looking at star-forming regions at different ages, or are we looking at stars at different ages within those star-forming regions?
Yes, yes. Well, your IFAS sample, can you remind us which region was it, or which sample was it? And can you pull up the scatter plot again? So we look at the...
this one?
Yeah, maybe. So yeah, which regions are in here?
I would need to check. I really don't know. I would need to check the venue.
But you have ages there, in fact, up to 7.4.
Yeah. So 7 is 10 million years. So there are stars here at 20 million years. Yeah. But how reliable the ages are, that is a different question, I think.
Yes. Any other questions on the accretion rates and metallicity dependence of accretion? I mean, the high mass end is even more problematic to measure accretion rates. We're trying to do that from the outflow. There are outflows as well. But I think you had a graph as a function. Yeah, it's here, stellar mass. So you have some accretion rates here up to 10 solar masses. Am I reading that right?
This is 10, yeah. This would be 1.
So you do have intermediate mass stars here with measure. Well, actually, those
Yeah, this is a Hartmann sample, so I check what those are. But there are heroic stars up to 10 solar masses where you can measure mass accretion rates, and they do follow the relation. Yeah.
Well, maybe we can come. Let's go to Devesh's question next. We can switch topics to the very massive side.
Hi, Professor Wayne. Thanks for the great talk. I just was wondering, on the HR diagram, you showed this downward evolution. Could you kindly explain a little bit more? At what time in the evolutionary stage is this happening? it's kind of like the Wolf-Rayet took, is it? Is it like an advanced nuclear burning stage or?
No, sorry, I should have been clear. This is the zero age main sequence. So
Oh,
because these stars are already when they're forming, and well, if the zero age main sequence is a real thing, so as if really there is a point where you can really identify this is H equals 0, this is where the hydrogen star is burning, and I have exactly this kind of mass of the stars, if I'm 500, 400, 300, yeah. That is immediately, because it's above this transition point, it immediately has a huge mass loss rate, so it immediately comes down. Yeah? So this is during the hydrogen burning. Then it runs out of hydrogen. It's completely removed its hydrogen here. And here you get the helium burning phase, classical Wolf-Rayet phase, and you have a similar effect. Again, you have very high mass loss rates. You have vertical evolution here too. This vertical evolution is in many different tracks because of strong Wolf-Rayet mass loss rates. People have used Nugas and Lamas in the past. We use hydrodynamically consistent models from Sander and myself. But both show this vertical evolution in the Wolf-Rayet phase. This is normally not included. People normally have lower mass loss rates, and they would normally go that way. The problem is, when you go that way, you cross the Humphreys-Davidson limit, and we have no observed stars there. So nature apparently doesn't like it, no, that the stars would go that way. No? So this is one potential solution to that problem. These stars just don't inflate as much to get in that regime.
So can I ask here, I mean, the 1,000 solar mass track, I think you were saying it evolves by about 1.5 million years. It's down, it's lost most of its mass. So the mass loss rate is, what is it, 10 to minus 3 solar masses per year.
Yeah. Mm-hmm.
But obviously, if you'd started at 200 solar masses, the mass loss rate would be a lot lower. But is the instantaneous mass loss rate a measure that is distinguishable? So we could tell, oh yeah, this was 1,000 solar masses because it's got a high mass loss rate rather than initially 200.
Yeah, from the from just the mass and the luminosity of the star, you wouldn't know the difference. There might be some possibilities to break that degeneracy using the hydrogen and helium abundance. We wrote a paper with Aaron Higgins in 22. So this paper, 22.
I guess I'm asking if the mass loss rates are the same at this point as well, or
yeah,
if
the mass loss rates here are very similar. So you wouldn't distinguish at this point. You wouldn't distinguish.
Mm-hmm.
Look, I would still say if you had one star at this mass, which one is more likely, that one or that one? And because of IMF arguments, the 200 solar mass star is more likely. But it's not. You can't say. And I said 1,000. I mean, I could have picked 5,000. You would have just had much stronger mass, so you would have had the same effect.
Yes.
and sorry, just a silly question then, Professor. So what about then going to lower metallicities is what I'd naturally ask here, or extreme case at POP3. Will they also lose this great amount of mass already? Let's say the 1,000 solar mass star.
Well, there are two effects here. One is whether or not you become optically thick and you get the strong mass loss effect. Yeah. That is less metallicity dependent than your normal line-driven winds in the normal O-star regimes, which are strongly metallicity dependent. So it is still the case that at lower metallicities, such population 3, I would in principle expect much lower mass loss. Unless the stars are rapidly rotating or there are other ways of mass loss. But yeah, in principle, the mass loss rate should still come down with metallicity. And that to me means that definitely the effective mass goes up, but maybe even the initial zero-H main sequence mass goes up. If this physics is indeed the thing that sets the upper mass limit.
And sorry, Professor, the point about just crossing the Humphrey-Davidson limit. This is such an interesting result that if this mass loss prescription is absolutely correct, then you wouldn't form these red supergiant stars over certain solar masses, right? Because all of these stars, as you show, they kind of stay in the blue side of the HR diagram, right? The TF is so high, they end their evolution there, I'd assume, right? They never puff up.
These never puff up. These evolve this way and they end here.
Okay, thanks.
So how can we look for, if these things exist? I mean, we mentioned R136 and the claim there. Well, it's currently what 150 solar masses, but could have been initially 300 solar masses. That's what I remember hearing from Paul Krauser. Is that still the valid? Is that still a valid conclusion, York, on that case? And
just the 150 is old work by Feiger. Then in 2010, Crowder increased that mass, and that is the initial mass. Actually, sorry, the current day mass is increased. So the actual measured mass has gone up because of a difference in temperature and reddening treatment. And it has been calibrated against binaries as well. Now, the R136, the most massive one, is not a binary. So the specific number there will still always have some uncertainty, but it will definitely be 220 to 260 currently. The 300 then came from, he had a present day mass of 260, and because of prior mass loss, he said the upper mass limit is about 300. And I say the current day is 260. The upper mass limit could have been 300, but it could have been 1,000, and I just can't tell.
Yes. But how do we know the age? I mean, do we really know the?
We have some handle on the age via the helium abundance. So hydrogen is a bit like a clock. Yeah, normally you can't do that because the clock ticks in the center of the star, because the outer envelope doesn't know anything. But above a certain mass, the stars have such huge convective cores, and because of strong mass loss, that little bit of radiative layer on top is basically gone within no time. That means that the entire star is like a core. So the surface, hydrogen and helium, is the same as the core. So suddenly you have an actual clock. And that is the way that we have been trying to get, for a few stars, it's possible to learn a bit more and to maybe break this degeneracy.
So there is a constraint on the age from helium abundance in that star in R136?
Yeah, there is a constraint, but I wouldn't call it a very strong constraint yet. The accuracy is actually pretty good, I would say. The physics isn't very complicated, so I think we have pretty good accuracy here, but we don't have very good precision.
And there's only one star in that regime where helium is a clock, or is there more than one star?
That was a binary, R144, if I remember correctly. I would need to go back to the paper, but if you want to know more about it, Higgins 22.
Yeah, because if you have two, of course, then it's very good to have a relative. But then, which is so? If we have to go beyond R136 to, I don't know, a more massive cluster, young and revealed, which is the best target for finding, similar stars or better stars, more massive stars?
There are some studies, extragalactic studies. There's NGC 3125 comes to mind, where people have looked at clusters which clearly have helium-2 emission signatures that are basically the same as you see with the stars in R136, and which I've shown that basically when you kick up the gamma, higher mass star, higher L over M, you go from weak emission lines to strong emission lines in helium-2. And Crowder has shown that if you look at R136 and you integrate the light from just the normal stars, the 70 or so O stars, they're all in absorption. And the 7 very massive stars, 7 of them, they rival the O stars in their overall flux, but it's those stars that uniquely have this helium-2 signature. And the O stars won't produce that. So it is that signature that teaches us that there are very massive stars present, also in regions where we cannot have individual stars resolved. So there are a number of galaxies now where these signatures of very massive stars have been seen from the helium-2 emission.
Now, you mentioned the nitrogen enrichment, which of course is quite interesting for high redshift. So any thoughts on what, from your point of view, what would be needed for this special nitrogen?
Yeah, in my view, it is putting the pieces together. So we get a little bits of information from many different parts of the universe are teaching us different things. I think the very massive stars are a very good candidate for producing this nitrogen emission, but there are other candidates like rotating Wolf-Rayet stars, supermassive stars, if they exist, and perhaps other sources as well. But I think the combination of basically population synthesis and galactic chemical evolution, including these very massive stars, will probably teach us more firmly what the role exactly is.
Right. If there are other questions, please, people jump in here. But I can keep. We can otherwise switch. Well, I'm interested in the black hole production, of course, as well. And now I'm trying to understand the implications of your high mass loss rates on various theories for producing supermassive black holes, many of which involve growing a star through, a very massive star phase. And if you're telling me that a very massive star is rapidly going to become just a massive star because of this high mass loss, that may make it difficult to grow through this intermediate mass regime, this very massive regime. So is it the case then that this mass loss rate is just getting more and more extreme? It sounds like as I go from 1,000 solar mass star to 10,000 solar mass star, just because I'm getting so close to the Eddington limit there. Is that basically what's happening?
Yeah, I would imagine that it is if the mass loss if this happened at solar metallicity, then I would think it would be very hard to get supermassive stars. Supermassive black holes from supermassive stars or something. But at lower metallicity, things might be different.
Right, but how different? So, because of course, zero metallicity you mentioned it is quite different, but I guess it's all a question of what kind of mass loss rates we're talking about. But certainly LMC metallicities, you're saying can do it. And once you have, and then you mentioned this optically thick regime where it wouldn't even really matter too much. Is that right?
That's right.
So let's see. So even the metal-free case approaches this optically thick regime, or not?
I'm not entirely sure about population 3, really. It is just that the mass where this regime occurs, of course, goes up and up and up with lower and lower metallicity. So it could well be that in the POP3 regime, you never reach that optically thick regime. But I think there are other issues we need to consider. And also, I made it sound as if everything is sorted. Of course, these are all 1D models. Yeah. And whether or not stars inflate or not, in 1D, they inflate. But in 3D, they might inflate less. So there's other physics that becomes relevant for these high L over M situations.
Well, and certainly the rotation is important, but that only increases the mass loss rates.
Sorry?
We mentioned rotation briefly, but that only increases the mass loss rates, as I understand it.
I would think so, yes. Especially in itself, not necessarily. If you just had a normal O star and the star is rotating, I'm not at all so convinced that the mass loss rate would be increased. But I think if you get close to the Eddington limit, basically the rotation basically helps you to get to the Eddington limit sooner. This is basically what Meyer has shown.
Yeah, Devesh, do you want to comment on that?
Yeah, I was just wondering, Professor, the same thing, really, right? First, the L over M is kind of constant, right? Like after a certain mass or luminosity or so, they're all at Eddington limit. They're like 0.9-ish or so. And the higher masses you go, they're kind of pretty much there. They never, of course, approach one. And the other thing with rotation is that they also make the structures more compact. So that makes a star, maybe, yeah, it's not as clear cut as you're saying. I think. That's what my silly interpretation would be of this, that it's not always aiding.
Yeah,
Mhm.
that's right. Also, of course, when we talk about the Eddington limit and talk about it, always realize that gamma is depth dependent. It depends on radius. Uh, so we often use gamma E, the electron scattering gamma, because it's a convenient parameter. And you can compare two stars with different masses and luminosities. As long as the gas is ionized, gamma E plays like a stellar parameter. But what really sets the physics is the total gamma, with all these line opacities included. And that is not just one number, even for one star, that varies throughout the atmosphere of the star.
Mhm. Great. Well, I know we're going to finish soon, but you showed a graph which was the end product of stellar evolution and this boundary of pair instability, which you said is a new result. Perhaps you can pull that slide up again. I think it was showing to, yeah, this.
Yeah.
Well, so I'm reading the x-axis as metallicity, am I? And then,
That's metallicity. Yeah.
and then, so can you remind, what do you mean by this new limit? Is that to do with some other physics?
Yeah, this is so to do with some other things. So basically, prior to this event, yeah, the general expectation was that in the regime below pair instability, the heaviest black hole will be about 50 solar masses. And that is because a core of 37, we find it to be at 36, but okay, call it 36. A CO core of 36 solar masses will go during oxygen burning will produce these electron positron pairs, and then the pressure support is gone and you collapse. And that means that the sort of, yeah, in that regime, somewhere between 37 and 50 or so would be the upper limit. But then this event happened, you have an 85 solar mass black hole here. Now, of course, this is possible that it had an earlier merger of, I don't know, 35 and 50 or so. But getting one merger in the age of the universe is already hard. To do it twice is quite significant. We were wondering, is it not possible to create this from single stellar evolution? Can a single star really not make an 85 solar mass black hole? And what turns out, where we don't know much about is actually about the core boundary mixing in massive stars. So we know the convection quite well, but the overshooting region, the region between the convection and the radiative layer, is not that well constrained. And if you vary that parameter, then you can have much larger or smaller cores. And what you need to do basically to get an 85 solar mass black hole, you need to, on the one hand, you cannot have too high an initial mass, because if you have a huge, say 200 solar mass star, will have a huge core, even without overshooting. It will be more than 100 solar mass core. So that will never make a black hole. It will always go pair unstable. So you need to stay below about 100 solar masses. If you stay below 100, but above 85, of course, because you need to still in the end make an 85 solar mass thing. So you have a limited range between about 85 and 100 you can play with. And that is indeed where we are. We are in the range of about a star the size 90 solar masses, can have a core just below the critical CO core mass of 36 solar masses. And it can then still have a relatively large hydrogen envelope on top, which is even larger. The mass in that envelope is larger than that of the core. And if you maintain that, like in solar metallicity, of course, because of the strong winds, you would remove that hydrogen envelope, as you would never make an 85 solar mass black hole. But if you drop your metallicity to less than a tenth, then you are in a regime between 85 and 100 solar masses at low metallicity, where you could potentially get 85 solar mass black holes. And that is what we call here this new limit at 93. And that is twice as high as people previously considered.
But so I didn't quite realize it had to have come from a star which was not much more massive than 100. So it's quite a narrow range.
Yes, a very narrow range, yeah. Now, if you go to really massive stars again, above the parent stability, then you might still get intermediate mass black holes.
Yeah, and well, but they would have to survive their mass loss to do that, yeah.
Exactly, so that would have to be at low metallicity.
Very good. Well, I know we have to finish in a couple of minutes, so if there are any last questions, now's the time. If not...
About the nitrogen, if I may. Sorry,
please.
Yeah, you mentioned, of course, VMS are very good candidates. It's your last year's wonderful paper, and I was just wondering, the mechanism is really just this mass loss that you showed, right? This downward trend in the evolution. So if you lose all the envelope of a star, I guess that's how you're getting nitrogen out, right?
Yeah, because as I said, they have a huge convective core, chemically homogeneous. You have a CNO cycle operating, you get nitrogen up, CNO go down, and in addition to the CNO cycle, you have this neon sodium cycle and a magnesium aluminium cycle. So whilst you increase the nitrogen, you also go up in your sodium and aluminium, which is the kind of patterns, nitrogen up, sodium up, that we see in globular clusters.
And sir, would you be able to also explain iron? Because that would be amazing. Can you also explain the FeO abundances? Because no one else, like no other models can do that as far as I know. And I think VMS would be like perfectly...
I haven't thought about the iron that much, to be honest. But that, yeah. So I'm just talking about the wind phase. I'm not talking about later evolutionary phases. And it's not a consistent chemical GCE model, of course.
Thank you, sir.
Very good then. Well, so let's thank Yorick again for a great talk and discussion.
All right then.